Hi everyone, in this one we're going to be talking about special products, which is what you'll find in lesson 7.07. So let's take a look at what are the special products that appear when we multiply polynomials and how are they recognized. We have two that we want to look at. I'm going to look at the first one, which is the answer we get when we do a problem like x plus 5 squared. All right, x plus 5 squared. Take a minute and think. What's your initial reaction there? Does that equal x squared plus 25? No. Most commonly, people want to just say that's x squared plus 25, but that is not the case because we know squaring, when you have an exponent of 2, like we see right here, that means something times itself. Something times itself. Well, the something that we're multiplying by itself here is x plus 5. So we're multiplying all of x plus 5 by all of x plus 5. That means we're multiplying a binomial times a binomial. And we know there's more to that than just the x times x and the 5 times 5 because we have to take the x and distribute it to everything in the other parentheses. And we have to take the 5 and distribute it to everything in the other parentheses, allowing us to set up x times all of that, x plus 5, plus 5 times all of that, x plus 5. So now that we have it set up, we can apply the distributive property. X times x is, don't forget when you're multiplying to add the exponents, so 1 plus 1, so that's x squared. And then we have x times 5, which is 5x. Then we have 5 times x, which is 5x again, positive. And then we have 5 times 5, which is positive 25. Now we can combine our like terms. The only like terms we have here are the two middle terms and two groups of 5x. Two groups of 5x combined to give me 10x. Just like the 5 squared gave me the plus 25, and the x squared, x times x, gave me the x squared. So when we multiply x plus 5 squared, we get x squared plus 10x plus 25. This is an example of a perfect square trinomial. So we have an example here, x squared plus 10x plus 25. It's a trinomial. Why? Because it has 1, 2, 3 terms. And it's a perfect square. Where else have we seen the word perfect square? When I think of perfect squares, I should think of numbers like 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225, 256, 289, 324. I'm out of practice. I hesitated there. But we could keep going, right? Because these are all perfect square numbers. Well, now those perfect square numbers, we know those are perfect squares because we got them by multiplying a whole number by itself. Something squared gives me a perfect square. Well, now we don't just have a perfect square number, we have a perfect square trinomial. Since we're talking about polynomials, we have a polynomial that is special. It's a perfect square because it's the result of multiplying a polynomial by itself. There's a pattern that exists so that we can identify these. That pattern is if we have a plus b squared, we know we're going to get a squared as our first term. Two groups of a times b is our next term, and b squared is our last term. So I could even go as far as to say if I had 4x squared and I had b squared at the end was plus 9, I could even figure out what value I would need to make that a perfect square trinomial, because I know the middle term would have to be 2 times, well, to get 4x squared, we know that's going to be 2x times 2x. To get 9, we know that's going to be 3 and 3. So the middle term is going to have to be 2 groups of 2x times 3. So 2 groups of 6x, which is 12x. So we've just figured out what value would make that a perfect square. The other special product that we're going to see is called a difference of squares. And what does the word difference mean? Difference means it's a subtraction problem of squares. Going back to what those perfect squares are, that's a subtraction of 2 perfect squares. Now, notice this isn't a sum, it's a difference. So this is only applicable to things like x squared minus 4. That's a difference of squares. We want to recognize a difference of squares because a difference of squares can be written as x plus 2 times x minus 2. Go back to what we know about multiplying. That would be x times x minus 2 plus 2 times x minus 2. That would be x squared minus 2x plus 2x minus 4. So what we see here every time is when we have that middle term, it's canceling out. And why is it canceling out? Because these numbers are the same, right? We've got 2 groups of the same thing, 2x and 2x, and one of them is positive and one of them is negative, leading me to 2 opposite values there. And that only happens if we have the same for one value, and then we've got the plus 1 and the minus the other for the other value. So a plus b times a minus b, that pattern will always lead me to an answer that is a difference of squares. And why is it only going to be a subtraction? Well, again, look at what we're doing. The only way we can cancel out the negative AB and the positive AB is by having different signs there, which means to get this value at the end, we're always going to be multiplying a positive B times a negative B, which is a negative B squared. So we're always going to have the A squared minus B squared when we multiply A plus B times A minus B. That's the special. It's only special if it's a difference of 2 squares.